Good morning, ladies and gentlemen. Time to get started. Welcome to week, whatever it is, 6. Are we in week 6 already? Is that possible? 6, yeah. Lecture 14, yeah. The announcements will come as no surprise today, especially once I can get them to move. You've got a checkpoint for the first 2 parts of your project tomorrow. You're well aware of this. There's no homework due this week, but homework will be assigned on Friday. So while you're finishing up your project, there will be a homework to work on as well on current material. Somebody pointed out to me that the readings haven't been updated. The book keeps being updated after every lecture. So what you should do is if you go to any part of the textbook, you scroll to the bottom of the page, there's an arrow that takes you to the next section. You can just keep going. And so, for example, the join and maps lecture that Professor De Niro gave, I wrote it up, and it's available there as section 8 point something, actually 7 point something. And then, for example, last time's Monty Hall lecture, which was very fast, and after the class was over, is there in section 8.3. That's where I want to start today. Before I get started, are there any administrative, bureaucratic questions? I am, with great relief, able to announce that our enrollments are finally done, and I can now focus on actually teaching this class. Okay, so technical issues with projects and so on, I can't get my server to wake up, I can't get this and that to happen, are best reserved for Piazza and your GSI. What we'll be doing here is we will be continuing on understanding randomness so that we can start simulating some serious experiments that enable us to get on to do inference based on random samples. So what I want to do, since last time we did the Monty Hall problem after the class was over by popular demand, what I'd like to do is I'd like to quickly go over it again and take a look at the code. And so that was our friend the goat. 3 doors closed. Behind one of the doors is a car. Behind the other 2 doors are goats. The contestant gets to pick a door according to a certain scheme, and the scheme is first the contestant gets to pick a door, and so say she picked door number 2. Then it is certain that behind at least one of the other 2 doors there is a goat. So Monty will open a door that has a goat behind it and reveal the goat. That's the Wikipedia goat right there. And so now you are left with 2 doors, one that she actually picked and the other which remains. And it's also true that behind one of those doors is a prize, and behind the other one is a goat. And now she has the choice of which one she asks to be opened. And the question is, does it matter which one is opened? And there was quite some debate about this. And we have a simulation. So what I would like to do is go back to that simulation. We defined 2 arrays. There's doors, and then there's goats. We had a function that we had defined a couple of lectures ago called other1, which takes an element and a 2-element array, and if this happens to be the first element of this array, it returns the second one. If this happens to be the second one, it returns the first one. If it's neither, then it says all bets are off. Okay, so now to simulate the game, we're going to have to play the game. So the contestant is going to pick one of 3 doors at random, and at that point, Monty is going to have to decide which of the other doors to open, right? Or which object to throw out, which goat to throw out. And for this, we need to identify whether the contestant is picking a goat or a car. And obviously, the contestant can pick car, goat 1, or goat 2. So there is a little function called isGoat, which just defines, is this thing a goat or not? That's all it's doing. So when you give it the door name goat1, it will return true. If you give it the door name goat2, it will return true. Anything else, it returns false, right? Even if for some weird reason you entered goat3, it will not be happy. It will just return false because it's not one of those goats. All clear? And so these functions, other1 and isGoat, are sub-functions that we're defining because we need to use this. We need to do this operation over and over again. So we run that, and I just want to make sure that this function does what we think it's going to do. So if we pick the goat2, then is that a goat? It's a goat. Okay, we're happy about that. So now what we're going to do is we're going to simulate this game. And so we define a function that takes no arguments. It just says simulate the game. And it has a couple of pieces. So first, there is a random choice from doors. That is right here. That's what the contestant does. If that random choice is a goat, actually, let me back up. In either case, the function is going to return a 3-element array. The first element is going to be the contestant's original choice. The second element is going to be what Monty throws out. And the third element is going to be what remains behind the other door. All clear? So we're going to return a 3-element array. Okay. The first part of the function says, if the choice is a goat, then return the following array. First element, the original choice. Second element, if they picked a goat, then Monty must throw out the other goat. Yes? So we will call the function other1 using the original choice and goat1, goat2 as the array. And so if they picked goat1, this will return goat2. If they pick goat2, it will return goat1. And the third, then, is what remains behind the other door. Now, of course, the contestant picked a goat. Monty threw out the other goat, and so what remains behind the other door must be a car. All okay? And right here in the code is the answer to your question. But should the person switch or not? Because do you see? Every time the contestant picks a goat, what remains behind the other door is a car. Yep? Now, what's the chance that the contestant picks a goat to start with? 2/3. And those 2/3 of the time, what remains behind the other door is a car. It's the same event. Contestant originally picks a goat. There is a car behind the other door. Those are exactly the same event. You can see that in the code. So, in fact, you should switch. The chance is 2/3 of being on the other side, but we can go ahead. The car being on the remaining door, we'll go ahead. Else. Okay. So, else, what is the else? If the if doesn't happen, then what else? What did the contestant pick? So, okay, when does the if statement get to here? If this returned false. Yep. If this returned false, what did the contestant pick? If isGoat original was false, what did the contestant pick? Car. They picked the car. So if they pick the car, then Monty has 2 goats to choose from. Yep. He's got to throw one of them out. And so what we're going to return is their pick, which is going to be the car. Monty's going to throw one of them out, and here we have just decided that he's going to throw one of the 2 goats out at random. Okay. And then what will remain behind the remaining door is the other goat. So I'm going to pause for a second. Please take a look at the code and let me know if you have any questions before we run the game. The 3 elements of the array that we return: first element, the contestant's original choice. The second element, the goat that Monty throws out. The third element, what remains behind the third door after that. Okay. So we'll define this function. And how about we just play this game once? Okay. So the contestant happened to pick the car. Monty threw out goat 1, and what remained was goat 2 behind the other door. And if we run this again, the contestant picked goat 2, what thrown out had to be goat 1, and then what remained behind the other door was a car, and so on and so forth. All clear? So now to see the proportion of times the various the prizes and goats remain behind each of the doors, we need to collect all of this in an array. As we are doing the experiment over and over again, and so here is the typical simulation. Every simulation that you do is going to look like this. So it is important to look at the pieces. First, how many times do you want to repeat the simulation? I've got 10,000 up there. You can change that number to 1,000 or 100,000. At some point, it'll get really slow. All okay? 5,000 you can repeat 2 times. By the way, when you are writing your own code, when you are writing your own simulation, I would start with 2. All right? Get it right for 2, and then it's going to work for 100,000, you hope, but don't start with 100,000. Okay, so now we are going to have to collect an array of original choices, a corresponding array of what Monty throws out, and a corresponding array of what remains, and therefore, step 2, create the 3 empty arrays. So right here, that's where we are. Questions up to this point? So this is all set up. Now start doing the thing over and over again. Okay, so doing over and over again, this is a for loop for I in range n, that is the numbers 0 through n minus 1, and therefore it will repeat n times. Okay, what's the first thing you got to do? The first thing you got to do is play the game. So you play the game. Remind me what this returns. Monty Hall returns what? A 3-element array. So you capture that in an array called result. Okay. So this is the result of a single game, and now you collect the pieces. Item 0 of result is the contestant's original choice. Item 1 is what Monty throws out. Item 2 is what remains behind the other door. And so the next thing that happens is you simply collect the appropriate item in the appropriate array by using np.append and overwriting the array every time so that it keeps getting longer. I'll pause for a second, take a look at that. And you're done. You have your answers. Okay? Now, what you need to do is visualize the answers. To visualize the answers, it's a great idea to make a table. And an obvious table to make is a results table with columns, original door choice, what Monty throws out, and the remaining door. And these three arrays that you made that are now filled with results. Every row of this table is one run of the game. And then we display. Okay, so questions asked now. All right, so before we run simulation, first decide how many times you're going to simulate. Create the empty arrays or tables where you're going to collect the data. Now, do whatever you need to do over and over again and append your arrays with the data that you have generated. And after that, visualize. Okay, here we go. So this takes a little while. I'm running 10,000 trials, not terribly long. And that's what I have. Those are my results. So this is the result of the 4th time the game was played. Contestant picked goat 2, Monty threw out goat 1, and what was left was car. And so what I would like to do is just see what remains behind this door here. Because we did have a discussion that says the person should switch. The person should ask for this door to be opened. And suddenly, if I'm looking at this column and I'm looking at this column, if I want the car, I want to be picking from this column. But that's only the first 10 elements. So what we'll do is, what do we call, results. So we were running into trouble last time because I forgot that bar graph doesn't group by itself. So we're going to group by a remaining door. If I stop there, what am I going to get? I'm going to get a table which has the counts of each category of remaining door. Yep. And so I'm just going to run that just to confirm. So car came up quite a lot of time behind the remaining door. And goat 1 and goat 2 appear almost equally. Horizontal bar graph of this table, these are the categories, therefore column 0. The remaining door contains the car about 2/3 of the time. The contestant ought to switch. This total is 1/3, and it's about 1/6 each. Okay, so while it is true that behind one of the two doors that the contestant chooses from, behind one of them is a prize and the other one is a goat, the two are not equally likely. And this is something to take away from this example. Just because there are two ways something can occur does not mean that each had chance 50%. And for example, if I asked you what is the chance that this room is going to be destroyed by the big earthquake before our class is over, then, well, the event can happen there are two things that can happen. Either it is or it isn't. Yes, you surely would not agree that the chance is 50%. If you thought that, you wouldn't be here. Yep. So just because there are two ways doesn't mean the chance is 1 in 2, right? Equally likely outcomes is an assumption that has to be based on something, and here that assumption is false. And if you want to have a non-simulation visual of why your contestants should switch, then a great way is this little table that I draw in Stat 2 all the time. The contestant can pick one of these three. No matter what, Monty throws out this, and what remains behind the door is this, right? And the only thing that's random is here. Everything else is determined. And so if you end up, as the contestant, having to choose between this door, and you want the car, which door are you going to pick? You are going to pick the remaining door. Okay. That's what's going on there. So what you've seen is a number of things here. First, that probabilities are interesting. They're not necessarily, as you would imagine right in the beginning, without giving it some thought. The other is that we have a way of simulating random experiments and getting approximations to probabilities without doing any mathematics, right? We hardly did any math. We didn't do any math here. We just did 1 out of 3 and 2 out of 3. And so that is going to be something that we will use, simulation, quite a lot. What I'd like to do today is develop some basic rules of actually calculating probabilities in small experiments so that you have some sense of how big numbers can get or how small numbers can get. And these rules will come as no surprise to you, I don't think. So basic rules of probability. Probability has a scale. Conventionally, the lowest value is 0, which means the event is impossible. Not just improbable, but impossible, cannot happen. Highest value is 1, also known as 100%, and that event is certain to happen. And then there are some basic rules of operation with probabilities, and one that you are, I am sure, familiar with is if an event happens with chance 70%, then the chance that it doesn't happen is the remainder, which as a percentage is 30%, equivalently 0.3. All okay? Yeah, no surprises there. And so now what I would like to do is I would like to look at an event that is perhaps a little more complex. So we're not going to be doing much programming here. So I have a red, a green, blue, and a green ticket, and in a box. This image of having a box full of tickets, shuffling and drawing, is going to be a very useful image from now until the end of the course. That is basically what you do when you draw a random sample. So I have a box with these 3 tickets. I shuffle and I draw 2 times at random without replacement. Can somebody describe to me what that means? So we talked about width replacement some time ago. What does this mean? So what am I doing? Yes? You don't put the tickets back in. So what's the first thing you do? Yeah, you're right. What's the first thing you do? You shuffle first, right? Random sample. Shuffle. You draw a ticket. You don't throw it back, so now next time you're drawing from 2 tickets. You shuffle those 2 tickets and you draw 1. Okay. And the question that I want to ask is, what is the chance that you have... how about green followed by red? Okay. And to answer this question, it's a good idea always to list the ways. And I think the pairs can be red, blue, blue, red, red, green, green, red, blue, green, green, blue. You agree? Anything else? You can't get the same ticket twice because you're not throwing it back. So how many options are there? There are 6, and with the sampling scheme, a natural assumption borne out by calculation is that these 6 are equally likely. If outcomes are equally likely, then the chance that some of them occur is simply a ratio. Which outcome do we want? This one. Yep. And that's 1 outcome out of 6 equally likely outcomes, hence the chance is 1 in 6. And so we've used something here that you use naturally, but I want to make a point of it, which is that if outcomes are equally likely, then the chance that something happens is the number of outcomes that make it happen divided by the total number of outcomes. So had I asked you, I'm rolling a die, what's the chance that it doesn't roll the face 6? You would have said 5/6. 6 total outcomes, which you are assuming to be equally likely because you don't know that I have a loaded die. Under the assumption that those are equally likely, the chance that you don't roll a 6 is the 5 non-6 faces divided by the 6 total. Okay. So back to our calculation, then the chance is simply 1 divided by 6. I don't want this to be a code at all. So that's this GR divided by, that's the number in this one set divided by the total number. That's 1/6. No big surprise there. What I would like to do now is to look at this 1/6 in succession. This is a 2-stage experiment. First you draw one and then you draw another. Now what is the chance that you draw the green first? 1/3 is the chance that you draw the green first. Yep. And so after that, you have to still do something more. So the first thing for you to notice is that the chance that you draw the green first, followed by the red, is going to be smaller than the chance that you draw the green first. Right? There's already only a 1/3 chance that you draw the green first. Now you're placing another condition. The answer is going to get smaller. And when you do probability calculations, I don't want you to try to plug into formulas. I'd like you to think about what happens to this chance. Am I asking for more conditions, therefore making it less likely to happen? Or am I doing something else? Okay, so now in order to think of the second stage, I would like you to imagine a whole stadium full of people, each of whom has this box in their hands. And the only people who get to stay and watch the game are the people who shuffle twice and get a green followed by a red. And for this... I had a lot of fun. I had a lot of fun doing that. Okay, so this is my stadium full of people. I didn't have time to draw all 60,000 of them. I just drew 6. Okay, each one of them has the same box, green, red, blue, and each one shuffles and picks one, and right at the first stage, these 2/3 need to walk out of the stadium. They've already lost. So 1/3 are remaining, and this is what you told me, 1/3 of the people are going to get a green ticket the first time. Yep. Now, they don't all get to stay. They got to play again. What is important for you to note is look at what's left in their hands. Right? Exactly the same tickets. Not just 2 tickets, but the same 2 colors. Okay, so now these people go again, picking from these 2 colors, and what's the chance that they get a red one? Well, 1/2. And this person, I tried to draw a really angry person because they got really so close, but no cigar. Okay, and so in the end, what remains is the fraction 1/2 of 1/3. And there's the multiplication coming in. And there is a formalization of this notion that we said that as you put more conditions on an event, the probability gets smaller. It gets smaller by a fraction of a fraction of a fraction of a fraction. It keeps getting smaller. And this is the multiplication rule, right? You start out with the chance that you draw a green ticket the first time. What do you multiply by? True or false? You multiply by the chance that you get a red ticket the second time. No. You multiply by the chance of getting a red ticket the second time among the outcomes that gave you a green ticket the first time. Yep? So the second one is a fraction of this first one. And so that multiplication must take into account that you've only kept a certain fraction in the beginning. And as we do these calculations, it'll become quite natural. I don't want to go into formalization. That's not going to be an issue for us. But I want you to have this picture very clearly in your head, the fraction of a fraction picture. And while we're about it, why don't I ask you a different question? So why don't I ask you the chance... Same experiment. These 3 tickets, I'm going to draw 2 at random without replacement. And I ask you for the chance of getting 1 red and 1 green ticket among the 2 that I have drawn. My first question before we get an answer is, have I asked the same question as before? Same answer as before, different answer. So if you have doubts about this, what I would like you to do is imagine that you get to play this game. And if you win, I'll give you $10, okay? And I'm a nice person. I give you a choice of games, okay? Your first choice to pick is the game where you get a green ticket the first time and a red ticket the next time, right? That's one game. The other game that you could pick is you get one red ticket and 1 green ticket, okay? Do you care which one you pick? Yes, suddenly you care. Yes, you care because why? Because the second one has more options of giving you a win, does it not? The second one doesn't care in which order the tickets came, right? So if you win the first game, you also win the second one, but you can win the second one if you've lost the first one, right? Second game is better. And what you have done in your head is you have partitioned this event, 1 red and 1 green, into 2 distinct ways in which it could happen. And those ways are... And you're happy if the event comes up green followed by red. You're also happy if the event comes up red followed by green. And look at this. You are now a person who is easy to please. You'll take this, you'll take that. You're an easygoing person. So what happens to the probability that your wishes are satisfied? Goes up. And so when you take a complex event and you partition it into distinct pieces so that your event can happen in exactly one of those ways, not some wishy-washy partition where this could happen and that could happen as well, but actually a clean break, then the chance of your event, well, what do you think? You're now satisfied by 2 of these strings out of 6, so the answer is 2 in 6th. Yep, which you can also see is the chance of the first one plus the chance of the second one. And it matters very much there that you partitioned cleanly. Okay? So, for probability theory, there is a times rule and a plus rule. And that's it. There are no other rules. So everything that is happening from this class upwards to Amazon doing machine learning to make sure that you get your shirt on time is based on these 2 rules. Right? It's just a question of using them in an appropriate manner. And so what I'd like to do is do one example where we have to figure out a combination of rules to use. And before I do that, let me just make sure. So we have a multiplication rule. The chance that two events both happen is the chance that one of them happens times the chance that the other one happens among the outcomes where the first one happened. And the answer is smaller than each of the two bits, as we discussed. And correspondingly, you also in the other direction, you also have an addition rule. And if you have partitioned an event into exactly two ways in which it can occur, then you can add up the chances to get the chance of your event. It is important that you partition. By partition, I mean two ways, only one of which can happen. And of course, this answer is bigger than the chance of each of the ways. It will come as no surprise that you can extend this to 3 events, 4 events, 5 events, which we will do quite naturally. And so what I would like to do now as an example is the chance of at least one head in a bunch of coin tosses. And it's not just a technical example of using the rules, but here is how it comes up in data science. So frequently, you will be working with data from random samples, and this random sample has come from a population. Okay? What you are interested in is whether the random sample sort of represents the population. Okay? And the groups in the population that you are going to be most worried about are the groups that are rare in the population. Right? If you pick a sample, are you going to pick up rare elements of the population? That is a question that arises quite frequently. Because you feel that if you just pick 2 people from your population, you won't get a rare one, right? Maybe if you pick 20, you have a better chance of getting a rare one. How many do you have to pick to have a significant chance of getting a rare one? This question occurs quite a lot. And so to answer this, it is important to be able to deal with questions like, if I toss a coin a bunch of times, what is the chance that I pick up a head somewhere in there? If I roll a die a bunch of times, what is the chance that I pick up a 6 somewhere in there? Because if we can answer that question, then the same thing with different numbers will say, if I have a population and only 1% of the people are of this sort, what is the chance that I pick up at least one of them in my sample? It becomes the same question. And that is why we are going to take this question as an example in this lecture. And if I have, what I'd like to do first is start with 2 tosses. And 2 tosses, you agree, can land exactly in those ways. There is no other way 2 tosses can land. And when I say coin, you can just assume that it's a fair coin. Each face is just as likely as the other. So then you can assume that these 4 outcomes are equally likely. So what is the chance that you have at least one head? Up there. So what are you going to use here? I've asked you for a chance. You have all the outcomes laid out. We have discussed that they're all equally likely. What are you going to use? A ratio. You're going to use the equally likely outcomes probability. You're simply going to count how many outcomes give you at least one head. How many outcomes is that? 3. And so the chance is 3 out of the 4 outcomes, 75%. Yep, terrific. So that is one use. But something else that you observe is that it's really all outcomes except this one. Yes? So if I could just figure out the chance of those 2 tails, I could subtract from 1, could I not? And I would end up with the same answer. So now figuring out the chance of those 2 tails with all the outcomes written out beautifully like that is clearly 1 out of the 4 outcomes. And so it's 1 minus a quarter. Yep. Can you use the multiplication rule to give me the quarter? What's going to happen? Yeah, I know a quarter is 1/2 times 1/2, but what's that got to do with anything? Okay, so one of the things I'd like you to be able to do is to articulate what the bits of a calculation mean. It's not enough just to have the numerical answer, because unless you can articulate that, you can't use it in a more complex setting. Right? So the chance of both tosses landing tails is going to be done how? I know this is easy, but you've got to be able to say it in English. It's the chance that the first toss lands tails times what? The chance that the second toss lands tails. Thank you. Somebody was paying attention. Given that the first toss landed tails. Remember the multiplication rule, please. Do not forget that one. In this particular instance, the second toss is not influenced by the first toss, and so the chance that the second toss is a tail, given that the first one was a tail, is the same as if you were given that the first one was a head, or is the same as if you were given nothing at all. Right? In this case, there is a simplification. But in other cases, there need not be, as we found, where there was a drawing without replacement. So the second factor is the chance that the second toss is a tail, given that the first one was also a tail. Now, of course, that happens to be, in this case, 1/2 as well. And so what you are doing is you are computing 1 minus 1/2 to the power 2. You agree? Yes? Okay. And the beauty of this method is that you can extend it to any number of tosses. So with 3 tosses, if I want the chance of at least one head, then you'll agree that it's any outcome except 3 tails in a row. What's the chance of 3 tails in a row? 1/2 times the chance of getting a tail, given that the first one was a tail, still 1/2, times the chance of getting a tail, given that the first 2 were tails, still 1/2. So you have 1/2 times 1/2 times 1/2, that's 1/8. And so the chance that you want is 1 minus that. That is 7/8. Yep. And now that there were 3 tosses, well, there could have been 10 tosses, and our calculation would have been very similar. It's 1 minus the chance of 10 tails in a row. Yep. So the chance of something happening at least once is the complement of it not happening at all. Not happening at all is usually an easy chance to find. And so very often we will calculate chances like the chance that this person appears in my sample is 1 minus the chance that they don't appear at all. That one's usually an easier chance to find. Okay, so if you can do this, then surely if I ask you the following question, I'm going to roll a die, how about 4 times? What's the chance that I get the face with 6 spots, at least one? Please talk to your friends and neighbors and sort it out. Question to you. How many 6s could you possibly get in these 10 rolls? What's the smallest number of 6s you could get? 0. In 4 rolls. 0. And what's the largest number you could get? 4 rows, so you could get 0, 1, 2, 3, 4, 6s. Yes? Okay, you want the chance of which of these? 1, 2, 3, or 4. Yes? So you want a chance of a whole bunch of these. What's left over? 0. That seems a lot easier. Yes? And so that is why we look at the chance of zeros. Students always ask me, how do I know to do 1 minus? You know to do 1 minus when what's left over is simpler. Right? That is the rule. There is no other rule. You cannot do it by catchphrases like at least or at most, because I can give you at least 9 and then you won't want to do 1 minus. Right? You use 1 minus when the event that it doesn't happen is actually an easier event. Okay, so we are now going to look at the event of not getting any 6s at all. Okay, so this is a multi-stage event. You have 4 trials and something's got to happen on each stage. What has to happen on each stage? No 6s. Every single stage, no 6s. The minute you can write down at every stage what has to happen, you've got a product of probabilities. Right? This has to happen, and that has to happen, and that has to happen, and that has to happen, a fraction of a fraction of a fraction of a fraction. And in this case, happily for you, the fractions are all 5/6. Yes? And so the chance that you do not get a 6 at all that's the chance of not getting it on the first row. This is the chance of not getting any 6s in all 4 rows. And then 1 minus that is the chance of getting a 6 or maybe more somewhere in the 4 rows. And so that's a calculation that we can do, and it's just over a half. And now what I would like to do, actually I will stop and I'll take questions on the calculation. And then I want to see what happens as you increase the number of rows. Yeah.
Why wouldn't it be 1/6?
The answer? Why is the answer not 1/6?
Like, why wouldn't you use 1/6 to the power of 4?
1/6 to the power of 4 is the chance of getting a 6 every single time. Yes? That's actually part of my event.
Yeah.
Yes? I actually want that. I don't want to leave it out. Every time you have a minus, you're leaving that out. I don't want to leave it out. The only thing I want to leave out is non-6, 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 non-6. Okay. So what I would like to do now is just, you notice that we are doing 1 minus 5/6 to the power number of rows. And we're going to gather that in a table. I'm going to look at how that answer changes as the number of rows goes from 1 through 50. And we collect the answers in a table. So we have the rows in 1 through 50, and the chance of at least 1/6 is 1 minus 5/6 to the power the number of rows. And we have a table. Okay. Chance of at least 1/6 in one row is 16.666%. What is that? That is 1/6. That is a correct answer. We're happy with that. 4 rows, just above 50%. That's what we said. That's our answer right here. Right? So we have the answer right. Look what happens to the chance. It is increasing. As you increase the number of rows, you are increasingly likely to see a 6 somewhere in there. And the rise is rather rapid. If I do results... It's almost certain by 50 rows. So at 1 roll, the chance is only 1 in 6. By the time you have 50 rolls, you're almost certain to pick up a 6 somewhere. And this extends to data science. Is if you have a sample size is small, then you will have a small probability of picking up elements that are rare in the population. But as you increase the sample size, that chance gets larger. And you can see, because we have a math relation, potentially, if you have the mathematics, you can figure out how big should the sample be so that I have at least this much chance of picking up groups that are this rare. Right? Because you have a little calculation that you can use. Now, we won't be doing something as detailed as that, but you can see that this builds up very easily to answering questions of that sort. Yes? Why did I choose 50 just because? Because I went up to 50 here. That's my own knowledge. I know that this thing rises rather rapidly, right? And so for you, you would have to run a few and just look at the answers. Okay? Yes? Is there a way to find these chances for outcomes that are not equally likely? Absolutely. You should be taking the Stat88 connector. Or I'm teaching 2 probability courses next term. Welcome. Okay. More. All right. So now that you have a handle, yes?
Explain the diminishing returns.
It's not diminishing returns. It's increasing likelihood. Do you mean that the chances aren't increasing that much?
Yeah.
Well, once, you see, the chances go from 0 to 1. Yep. So once you're close to 1, you don't have that much further to go. Right? So chances will plateau out at 1. I think that, am I addressing your question? Or, yeah, okay. And what you are noticing, though, is that the rise is very steep because it's exponential. It's a power. All right, so what I want to do now for the remainder of the class, which I don't have much of, is to talk about sampling in general. And for this, what I'd like to do is I would like to remind you of a data set that you have seen before. These are your movies, and now I have row indexes. And what I would like to tell you is that you have been taking samples all along. Have you not collected rows of this? You've collected rows of this by using where, by using take. You have collected samples, right? Those have been what are called deterministic samples. So nothing random about them at all. For example, top.take which indices do you want? How about 17, 83, and 121? How about that? There's your sample. You've got a sample. There's nothing random about it at all. Okay. You could have done top.where title contains one of the franchises. How about this guy? Okay, there's another sample. Perfectly deterministic sample. The reason I'm telling you this is the word deterministic. Deterministic means not involving any chance at all. Okay? But what we're going to want to do is choose a sample at random. And I will just simply stop here. On Wednesday, I will define a random sample, and then we will work by simulation with large random samples.